Another way that we can examine these systems that are composed of two components and their basically their vaporization process is to look at temperature composition diagrams. Now, remember the other one that we looked at was pressure composition diagrams, and so what we've done essentially is look at several different cross sections of the phase diagram for this binary system. So in the case of temperature composition diagrams, it's not quite as straightforward as it is for pressure, because we had a ready way of getting access to the pressure via the mole fractions. Okay, I'll remind you that we're going to assume that the second component is the one that's more volatile, so it has the higher vapor pressure for its pure substance. We also have derived this expression for the total vapor pressure for the binary solution in terms of the two components, the pure vapor pressures of 1 and 2, and the mole fraction of component 2 in the solution phase. Now, one of the things that we're going to need to do is solve this expression for x2, and so let me go ahead and write that down. If we were to solve for x2 out of all of this, we would subtract p1 star from both sides, so we would get p tot minus p1 star, and then we would divide that by p2 star minus p1 star. So we could express the mole fraction of the second component if we know all these pressures, and 3 of them actually are pressures that are determined by the identities of the components themselves, and the 4th one is the total pressure of our mixture. Now, these pure component vapor pressures are going to depend upon temperature. We know that already from studying phase transitions and phase equilibria. So these are all going to depend on temperature. All right, and how they depend on temperature is, going to change from substance to substance. We don't necessarily know that in advance. So what I'm going to suggest is that we're going to put together a prescription for a way to look at the variation of our vaporization curves with temperature. And this is the prescription that we're going to follow. First, we're going to use some means to find the vapor pressures of the pure substances at some temperature. So in other words, we're going to identify a temperature that we're interested in. So maybe I should put that first. Set the temperature that we're interested in, and then find the vapor pressures of the pure components at that temperature. Then we're going to use this expression that we've just written down for the mole fraction of the second component and evaluate what the value of x2 is. All right, at this point we will have our temperature and we'll have our mole fraction. So now what we want to do is graph these against each other. So the third step is going to be to graph the point that is made up of the mole fraction and the temperature. And that will begin to build a curve for us that will tell us how, how the vaporization point is going to vary with that temperature. Now there's a few things that we need to bear in mind here. First of all, what's happening with pressure? All right, for all of these things we're going to hold the pressure constant. So that means we've got to choose a pressure at which to hold these things constant. Now the one that makes the most sense probably is to use as ambient pressure the pressure that we would normally find in a room. So let's do that. Now I'm going to use the bars instead of atmospheres. So our constant pressure, which will represent P total in this case, will be 1 bar. And since we often measure these things in torr, I'm going to go ahead and translate this into torr. 1 bar is roughly equal to 750 torr. You may recall that 1 atmosphere is 760 torr, so they're very close. 1 bar and 1 atmosphere are just about the same pressure. All right, so this will be our constant pressure throughout. And the other thing that I want to make a note of is that this will be the pressure at which our solution will boil. So what we're looking at is, if this is our ambient pressure, what we're looking for is the temperature of the boiling point for our solution. But that boiling point will vary depending upon the composition. All right, so how do we set this up? Well, when we have our second component as the more volatile of the two, what does that mean for its boiling point temperature? Well, the temperature of the vaporization of component 2 versus the temperature of vaporization for component 1 it turns out is less than. Why is that? Well, if it's more volatile, that means it's easier to lift it into the vapor phase, which means we don't have to heat it up quite as much as we would have to heat up component 1 to get it to the vapor phase. So whenever you have a more volatile component, its boiling point is actually going to be lower than the less volatile component. So in this case, we're always going to have T vaporization for component 2 be less than T vaporization for component 1, as long as I am insisting upon this particular relationship between their vapor pressures. Now it turns out that these boiling point temperatures are going to limit the range of temperature that we can look at. In fact, we're always going to be interested in temperatures that lie between the two boiling points, because if it's below both boiling points, nothing's going to boil. So I'm going to have T vape 2 is less than, or I'll say or equal to temperature, and that's going to be less than or equal to T vaporization of 1. So if it's lower than T vape 2, nothing's going to boil. If it's above T vaporization of 1, everything boils. It's all going to be gone. So we want a temperature that's in this middle range somehow, and these are going to be the temperatures that we use as we use this prescription. So what I want to do is find the exact composition that will boil at the particular temperature that I've chosen. That's what we're doing. It sounds really complicated, and I suppose it is the way I've explained it, but let me begin to construct a picture of the graph that we're going to want to create out of this. So once again, it's going to look a lot like the graphs that we did for the pressure composition diagram. We're going to make a little box here. We're going to have our mole fraction of 2 graph from 0 to 1. Okay, but now I'm graphing the temperature on the vertical axis. And I'm going to restrict the temperature using this range of temperatures. Now, remember that I've found that T vaporization of 2 is less than that of 1, so my T vaporization of 2 might be down here, and my T vaporization of 1 might be up here. So I'm looking at temperatures that are going to lie basically in this range to examine this cross section of the phase diagram. All right. So as an example, let's do a quick example. Let's assume, as I have up above, that our total pressure is just 750 bar. Okay, so that's 750 bar. Now let's suppose that for the particular substance I have at a temperature of 350 K, that the pure substance vapor pressure for component 1 is going to be 500 torr, and the pure substance vapor pressure for component 2 is going to be 1,000 torr. Okay, now let's think about those numbers. This is greater than that, so this is the more volatile of the two components. Because it's more volatile, it has the lower boiling point. All right, and the assumption here is, of course, that this particular temperature is between those two boiling points. And let's say that it's, somewhere in here. This represents 350 K. All right, so at this temperature, what I need to do is calculate what is the mole fraction for component 2, but I'm calculating it from the pure substance vapor pressures that I've found at this temperature, because these both correspond to this temperature. So I use the formula up here. P tot is 750, P1 is 500, and then in the denominator I've got P2 minus P1, so that'll be 1,000 minus 500. You'll notice I picked numbers that are pretty easy to use. Okay, so I'm going to have 250 divided by 500, or the mole fraction is exactly 0.5. Oh, what a miracle. 0.5. Okay, so we're right here in the middle. Now, the point that we're going to graph is this point here. So that is a point that lies on our temperature composition diagram, that lies on our curve. Now, if I repeat that for many, many points, what I would ultimately find, presumably, is some sort of curve that comes down like this, goes through that point, and ends up down here at this point. Okay, so it's a little, I've drawn it as a little bit of a curve, and that's probably appropriate. Now, having drawn that curve, what would be the mole fraction in the gas phase for this same substance, for this same system? Okay, I've already got the mole fraction in the solution phase is 0.5, so that's true for both components. For component 2, I'm going to need the vapor pressure of component 2 divided by the total pressure. Total pressure, I know, that's 750. The total pressure for component 2 is going to be the mole fraction times its pure substance vapor pressure. So 0.5 times 1,000, so that'll be 500. So this is actually equal to 2/3, so I'll just write that as 0.67. So in other words, at this same temperature, I would have to come over here to get the vapor mole fraction. Okay, you see how it works? And so this is very much like the tie line that we found in the pressure composition diagram. And if we were to graph this for each of the points that we find along this curve, and let me draw this perhaps in purple to make it stand out a little bit more. So if I were to graph these points for each of these points on this curve, I might end up with something that would look like this. All right, so we end up having a diagram that actually looks kind of like the pressure composition diagram, except the other end is up high, the component 1 end is up high, and the component 2 end is down low. And in this particular case, we have a little bit different interpretation. So for example, if I were to start down here, this is the solution phase. Okay, low temperatures is solution phase, high temperatures up here would be the vapor phase. So if I start down here with a solution that has this mole fraction for x2, it would have the same mole fraction for x1. As I raise the temperature up here, this is the point at which it would begin to boil. And when it boils, it would come over here, and this is the mole fraction of the two components that I would find in the gas phase when it is boiling at this point. So the lower curve is the solution curve, and it tells me the point at which boiling begins. And the upper curve is the vapor curve, and that basically tells me the composition of the gas that comes out of boiling. Okay, so you see the composition of the gas is not the same as the composition of the fluid that gave rise to it, because the two components will have different levels of volatility. All right, we're going to explore this a little bit more, because it turns out that this particular setup is particularly useful when we want to do fractional distillation.